Black holes are nothing new. If current scientific theories are correct, then they've been a part of the world since the universe was less than 1 billion years old. Today we are exploring just how large black holes can become, with the final answer near incomprehensible to us on our tiny scale. The smallest black holes ever found are just over 3 times the mass of the Sun. A binary star system called XTEJ 165500, for example, contains a black hole with just 3.8 solar masses. That may sound small, but remember that a single solar mass is 2 by 10 cubed 0 kilograms. Yet these elfin stellar mass black holes are dwarfed by supermassive black holes, one of which is at the heart of the Milky Way galaxy. Our own Sagittarius A has 4.5 million solar masses, the subject of history's first ever black hole image. But let's continue moving a little farther away. At 11 million light-years from Earth we find Centaurus A, the closest active galaxy. It was born from a collision between 2 smaller galaxies. This collision was so recent that the merger is still in progress, hemmed by an outer field of blue and luminous stars. But what's the largest black hole we've found to date? That goes to the aptly named TON 618, a quasar, an active black hole consuming material and surrounded by streams of particles, that outshines the galaxy in which it sits. TON 618 is as bright as 140 trillion suns and has a mass of about 66 billion suns. For comparison, all the stars in our galaxy combined share a mass of only 64 billion suns. That is, TON 618 is over 15,000 times more massive than Sagittarius A. That's a staggering number. Because our brains did not evolve with a need to understand such large figures, it's unlikely any of us could ever truly grasp objects of this magnitude. Yet for everything TON 618 may be, it isn't close to the black hole size limit. A new study decided to focus on a frequently overlooked category of black holes, those that go beyond the supermassive. This new class is called stupendously large black holes, SLABs. Giants on this scale would hold the equivalent of 100 billion suns or more. Nothing like this has ever been observed in practice, but they are theoretically very possible. However, it's difficult to explain how a SLAB would form because we don't yet have a good understanding of how supermassive black holes, or even larger objects, are created. We have only theories. One of these theories is the primordial black hole theory. The problem with the idea of feeding and mergers creating supermassive black holes is that, as material falls into the event horizon, this process releases radiation. The radiation then becomes a boundary for more material to cross and continue to feed the black hole. On the other hand, mergers, as I mentioned, do not happen frequently enough to give a clear explanation of supermassive black holes. In terms of numbers, the research paper showed that the upper limit for luminous black holes in a disk galaxy is about 5 times 10 superscript 10, 50 billion solar masses. However, non-luminous black holes could continue to grow beyond this size. While it's not really expected, primordial black holes could potentially have been as large as 10 superscript 17 solar masses, with the absolute limit of black hole size being a staggering 10 superscript 19 solar masses. This is about 10 billion times the mass of the Sun, the largest a black hole could ever grow. While SLABs have never been observed, they also haven't been highly studied. It's possible to observe a SLAB via one of their many gravitational effects. Because of their deep gravity, these black holes will cause lensing, or the bending of light as it passes through intense gravitational fields. They would also disturb the structure of galaxies and emit radiation in the form of heat and light. It's even been suggested that black holes on these enormous scales may help solve the mystery of dark matter. While in the process of ingesting new material, dark matter in the form of WIMPs, weakly interacting massive particles, could gather around the hole and create a halo. Radiation will spread as the particles interact with themselves and annihilate, surrounding the black hole by an otherworldly aura of gamma rays observable from Earth. If we ever do build great ships that match the speed of light, we could even visit a black hole, an instance to remind us the universe is a treasure.